topic Real Numbers. Heading Properties of Positive Integers. Euclid's Division Algorithm. In class 9th, we began the exploration of the world of real numbers and encountered irrational numbers. Here in this chapter, we continue the discussion on real numbers. We have two very important properties of positive integers. 1. Euclid's division algorithm. 2. Fundamental theorem of arithmetic. Euclid's division of algorithm. Any positive integer a can be divided by another positive integer b in such a way that it leaves a remainder r, that is smaller than b. Have you remembered what you have done while doing 17 by 6? We considered 6 as divisor and 17 as dividend, the answer as quotient and balance as remainder. You were arranged all as 17 is equal to 6 into 2 plus 5. Now compare A is equal to BQ plus R. See another example. 455 is equal to 42 into 10 plus 35. Compare it with A is equal to BQ plus R. For every positive number, there are the only integers Q and R satisfying the conditions A is equal to BQ plus R, where 0 is less than or equal to R is less than B. Euclid's division lemma. Given positive integers A and B, there exist unique integers Q and R satisfying A is equal to BQ plus R. 0 is less than or equal to R is less than B. Euclid's division algorithm for HCF. To obtain the HCF of two positive integers, say C and D, with C is greater than D, follow the steps below. Step 1. Apply Euclid's division lemma to C and D. So, we find whole numbers Q and R such that C is equal to DQ plus R. 0 is less than or equal to R is less than D. Step 2. If R is equal to 0, D is the HCF of C and D. If R is not equal to 0, apply the division lemma to D and R. Step 3. Continue the process till the remainder is 0. The divisor at this stage will be the required HCF. Use Euclid's algorithm to find the HCF of 4052 and 12576. Step 1. Since 12576 is greater than 4052, we apply the division lemma to 12576 and 4052 to get 12576 is equal to 4052 into 3 plus 420. Step 2. Since the remainder 420 is not equal to 0, we apply the division lemma to 4052 and 420 to get 4052 is equal to 420 into 9 plus 272. Step 3. We consider the new divisor 420 and the new remainder 272 and apply the division lemma to get 420 is equal to 272 into 1 plus 148. We consider the new divisor 272 and the new remainder 148 and apply the division lemma to get 272 is equal to 148 into 1 plus 124. We consider the new divisor 148 and the new remainder 124 and apply the division lemma to get 148 is equal to 124 into 1 plus 24. We consider the new divisor 124 and the new remainder 24 and apply the division lemma to get 124 is equal to 24 into 5 plus 4. We consider the new divisor 24 and the new remainder 4 and apply the division lemma to get 24 is equal to 4 into 6 plus 0. The remainder has now become 0, so our procedure stops. Since the divisor at this stage is 4, the HCF of 12576 and 4052 is 4. Notice that 4 is equal to HCF of 24 and 4 is equal to HCF of 124 and 24 is equal to HCF of 148 and 124 is equal to HCF of 272 and 148 is equal to HCF of 420 and 272 is equal to HCF of 4052 and 420 is equal to HCF of 12,576 and 4052. Euclid's division lemma algorithm has several applications related to finding properties of numbers. We have some examples of these applications. Show that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. Let a be any positive integer and b is equal to 2. Then, by Euclid's algorithm, a is equal to 2q plus r. For some integer, q is greater or equal to 0 and r is equal to 0 or r is equal to 1 because 0 is less than or equal to r is less than 2. So, a is equal to 2q or 2q plus 1. If a is of the form 2q, then a is an even integer. Also, a positive integer can be either even or odd. Therefore, any positive odd integer is of the form 2q plus 1. Show that any positive odd integers is of the form 4q plus 1 or 4q plus 3, where q is some integer. Let us start with taking a, where a is a positive odd integer. We apply the division algorithm with a and b is equal to 4. Since 0 is less than or equal to r is less than 4. The possible remainder are 0, 1, 2 and 3. That is, a can be 4q or 4q plus 1 or 4q plus 2 or 4q plus 3 where q is the quotient. However, since a is odd, a cannot be 4q or 4q plus 2 since they are both divisible by 2. Therefore, any odd integer a is of the form 4q plus 1 or 4q plus 3. So that is all about this subtopic. In next topic, we will see second property of positive integers, that is, the fundamental theorem of arithmetic. Till then, keep learning.